In this video we present FlexSense, a transparent thin input surface that is capable of reconstructing complex and continuous deformations without the need for any external sensing such as cameras. This allows for a variety of paper-like interactions on mobile devices and high degrees of freedom input. 16 transparent piezoelectric sensors are placed on the periphery of a thin sheet. The surface affords complex bend and flex gestures. The main contribution of our work is to take these 16 sparse measurements and reconstruct the detailed shape and deformations performed on the flexible sheet. Two new algorithms allow us to accurately reconstruct the 3D shape of the sheet in a way that has never been demonstrated before without external sensing. We use a data-driven approach where we capture raw sensor data alongside ground truth 3D shape data using fiducial markers placed on the sheet, a multi-camera setup, and an as rigid as possible regularizer for inferring occluded points. Notice how this ground truth setup is able to accurately reconstruct the complex deformations being performed on the sheet of paper. This is critical to provide training data for our algorithms. We propose two methods that efficiently reconstruct the shape of the foil. The first is a simple algorithm based on weighted linear interpolation that is easy to implement. For details, please see the paper. This algorithm already allows us to model complex bend gestures. The next algorithm is a more sophisticated machine learning based approach, which continuously regresses the vertex positions of the 3D mesh. Again, for details, please see the paper. We evaluated both methods with respect to the accuracy on a ground truth dataset. Both methods were capable of accurately reconstructing most of the shown deformations. Qualitatively, both methods performed equally well. However, our quantitative evaluation revealed that the machine learning-based approach yielded less error. We explored the concept of a transparent smart cover, which allows for paper-like interactions on tablet devices. The accurate reconstruction of the deformations lets the user physically peel or flip layers of the user interface. In this example, the user can naturally reveal specific parts of the original photograph to see the effect of an image filter. In this photo editing tool, the user peels off the topmost layer to access the underlying information. Here the user checks the solution of a crossword puzzle to verify their guess. As he struggles to find the next word, he peeks at the solution by keeping the cover lifted. With the lift and drop metaphor, the user temporarily brings up another application by bending the left edge, marks a region, and drops the content back onto the original application. The transparent foil could also be used to let users literally peek behind the scenes. The user can see the original footage of this video before post-processing. This application brings back the traditional ways of animating to digital keyframe animation. The user quickly flips between two keyframes to sketch the current frame. After completing the animation, the user can flip through the frames with a continuous bending motion. Our sensor can also be used as a high degree of freedom input device. In this physics playground application, we demonstrate dexterous 2.5D interactions with virtual physics objects. We implemented a novel game concept that directly maps the complex deformations of our sensor to a magic carpet. Pulling different corners or sides of the sensor results in different behaviors of the carpet, such as changing the direction of the flight or shooting at objects. The user has to flap the sides to gain altitude. We demonstrated FlexSense, a new thin film transparent sensing surface which can reconstruct complex deformations without any external sensing. We presented two methods for mapping a small number of sensors to a three-dimensional surface. Our fully self-contained setup provides new interactive possibilities.